Okay, welcome back to another video lecture for calculus, and this video is designed to support a calculus course I'm teaching this semester. So in this video we need to begin discussing the supposed chain rule, and to do that I'm going to show you some functions that are difficult to expand. And what I mean by that is that we normally, if I were to give you like a binomial and then like square it or cube it or whatever, you can write out all the terms, FOIL it out, and then eventually it gives you a polynomial, and you can just apply the general power rule until you have whatever derivative is required for you to respond with. Now, other functions are harder to do that with. For example, this thing here is a gigantic square root, because we have this denominator in the exponent of 2, and then we have a binomial cubed. And the easier way to write this is just that we have a binomial raised to a rational power. And the exact motions that have to happen here in order to quote-unquote clean this up, like in 1.5, are actually kind of difficult to do, and they don't really get you anywhere because you still have to know how to handle the composition of two functions at the end of it, which is very, very difficult if you don't have some of the tools to do that. So what I want to introduce to you is the chain rule, because the chain rule gives us a method in which we can take the derivative of something that looks like this, and we can actually do it pretty easily. So the way that I want to do this is just to kind of look at some of the Leibniz notations and see how we can put them together to arrive at our derivative. Remember, the goal is to get a derivative which is denoted dy by dx. And we're going to have to do kind of a tricky thing here in order to come up with that derivative. So if you try to do the derivative of this just as it is, there's no product here. It's not one thing times another. There is no quotient here. It's not one thing divided by another. And it's not easily expandable into polynomial form because you have a square root and then you have this big thing on the inside. And so you could probably get the first part of this derivative correctly, but doing the second part of this derivative, you may not have any clue that you need to do that until you have seen what this trick is. So I've wasted enough time. Let me just go ahead and tell you what the trick is. If we were to do what I like to call wishful thinking, we don't know how to take this derivative. It's what I would call quote-unquote hard. So let's look for something that will make, let's look for a function maybe that we know how to take the derivative of that's easier, that could tell us how to come up with the final product here. And in wishful thinking land, if this was just some variable to the 3/2 power, and I'm sorry, I've written that off screen actually. If this was just some variable to the 3/2 power, well then we have the general power rule for that, and we know how it works. So if I were to go through my kind of long process that we had before with this idea, we could use the little increase to u, which we would call du, and the little increase to y, which we would call dy. And what we would see is that when I take the derivative of this thing, because this is going to be a small increase in u and this is going to be a small increase in y, what we're going to end up with is a dy by du term. And that should make sense because all of the derivatives, what we've been doing with them so far is there's a cancellation that happens on the right hand side, and then the dy gets divided by whatever the d anything on the right hand side is, and we end up with dy over that thing. So this is going to be dy over du. But notice here that dy over du is not what the goal is in our problem here. It is not dy over dx. So we're going to have to do something to fix that in just a minute. But let's just go ahead and write down what this derivative is, because we can use the general power rule to come up with the answer. And the derivative of u to the 3/2 power, well, it'll just be 1 times 3/2, which is 3/2, and then 3/2 minus 1, which is 1/2 in the exponent. So that's that. Now what we want to do is come up with a way to map this problem onto that problem. Notice here that I kind of told you we're in wishful thinking land. And in wishful thinking land, basically what I'm doing is I'm just covering up this x squared plus 9, and I'm saying, well, what if it was just a single variable like u? Okay. Well, if it was a single variable like u, well, then we would get this. But notice that gave us dy over du. So what we have to come up with here is something that we can multiply this by that will give us dy by dx. And again, this is a little hand wavy, but if you think of these Leibniz notations like they're fractions, then you know exactly what you must multiply this by in order to get the final result, dy by dx. So we have dy over du. In order to get a dx on the bottom, well, we must multiply by something over dx. But we can't have any du's in our final product because the final product is just dy by dx. So to cancel a du off of the bottom of a fraction, we must multiply by a du on the top of a fraction. Notice here what's going to happen. The du's cancel, and I'm left with dy by dx, which is precisely what I wanted. Okay, so what does that mean for us? Well, the dy by du term is just this thing here that we calculated. But notice that u is basically just something that we've substituted. We've said that u is equal to x squared plus 9. It's basically the part that I covered up, and I said, I'm going to wish that this wasn't here. I'm going to wish it was something easier. So the wishful thinking part, whatever I covered up here, that's basically what we're setting our u equal to, okay? But notice that in that case, what dy by du is actually equal to is this stuff circled in pink. It is 3/2 times u to the 1/2. But we know what u is equal to. U is equal to x squared plus 9. Now that takes care of this term here, dy by du. Now we just have to determine what du by dx is. Well, notice in this line here, if I were to go through my derivative process the way that we began with, where I add a little increase to x and then I add a little increase to u, and I go through all the motions there and some stuff cancels out and I end up with a final result, what that's going to give us is just the derivative of u with respect to x. And notice that basically what that's telling you to do is just take a derivative of this. Okay, so what is the derivative of x squared plus 9? It's just 2x. But notice now, I have dy by du, and I'm supposed to multiply by du over dx, and I know what du over dx is. It's just 2x. So to finish this thing off, I should say this is multiplied by du by dx. To finish this thing off, all I have to do is plug in that multiplication by 2x, and that is our derivative. So in general, anytime you have a composition of two functions, I want to show you a very quick, I'm not going to call it a proof, but I'm going to show you kind of like a general formula for it, I guess, and I'm going to kind of show you where it's derived from. We can solve any sort of problem like this where we don't, I would call it a hard problem. We don't necessarily just know off the top of our head how to take that derivative because it's something to the 3/2 power, but that something is not just x. Okay, that's the key thing here, is that you have something to a weird power and it's not just x, it's something else, like there's a function or something in it that you can see. So you can clearly see that I have this function x squared plus 9 plugged into something like u to the power 3/2. In other words, I have one function, something to the power 3/2, and I've plugged a different function into it. We call that function composition from algebra. So I'll clean up the board here and then show you kind of a general formula that you can follow for this. This method is useful for solving things that look like this. If I tell you to take the derivative of a function that has been composed with another function, okay? So that function could be anything. It could be like sine of x, all right? And the sine of x derivative is just cosine of x, but what about if I told you to take the sine of 2x derivative? Notice that that's not just an x inside of the sine, and so that's probably going to trigger our chain rule, and we can use this nice formula that I'm going to show you in order to do that. So what we did is we said, wishful thinking, what if this internal function g of x was just u? Well, then what that would basically be is like saying, what is the derivative of the function ignoring the inside part? So what is the derivative of this? Okay? And so that's going to give us just whatever the normal derivative would be, whatever the derivative of the outside function is. And what I mean by outside function, and you see there's this big parentheses here, f is the like outermost function in this. In our previous example, that was what is just the derivative of something to the 3/2 power. Okay, well we know that. So we write it down. But then we change whatever that derivative is, where the x would normally be, we change that with whatever we wished away. So if we wish away g of x, then this will actually be f prime of g of x, okay? Then what we did is we said, okay, so this part right here, right, if I take the derivative of that, making this substitution, that actually gave me dy by du. So the way that I needed to fix that was by multiplying it by du over dx, and the move is always the same because remember the goal is for this left-hand side to end up being dy by dx. So what I had to do is say, well, what is the u part? The u part is just g of x, so what is the derivative of g of x? Well, it's whatever the derivative of g of x is. We call that g prime of x, okay? And that had the effect of canceling the du's out and giving us the final product dy by dx. So if you want to take the derivative of some composition of functions, this part right here, which I will circle in this yellow color, is a nice formula that will allow you to come up with the proper derivative. Now, a couple of key things here, and this takes practice. I can't just like tell you a correct way to do this because the function could change and then you have to kind of think about that. But anytime you have two functions that have been composed together to produce another function, like f of g of x, if you can break it apart and you can figure out which part of it is f and which part of it is g, then we take the derivative of f and we plug in g for x, then we take the g part, we take the derivative of it, and we just multiply what our result was by the derivative of g. So some people like to say this is the derivative of the outside function, plug in the inside function, times the derivative of the inside function. There's not really a cute way to say it, the way that there was with product rule or the way that there was with quotient rule. And some people like to do this in a tabular form, which I'm going to show you very quickly. Now the move is always the same thing. All that we're doing is we're wishing a piece away and calling it u. Then we're taking a derivative. That gives us dy by du, but then we have to fix the fact that dy by du is not dy by dx, so we have to multiply it by du over dx. So I want to show you this tabular method very quickly, and I'm going to write down a note here which is that the derivative of f of g of x is just f prime composed with g of x times g prime of x. And the example that I want to use for this is one that you can actually verify just by expanding it out, although you'll notice that since this is not a first order binomial, it will be a little bit annoying to go through all the motions of expanding this out correctly. And if you use the binomial expansion theorem, it'll be faster, but you still have to make sure that you've applied everything correctly. So rather than waste our time doing the expansion and then trying to do a polynomial derivative of this thing, which will be big and unwieldy, we're just going to apply the chain rule. Okay, so I'll go through this two different ways. The first way is going to be just using the formula for what it says, and then the second way will be this tabular method, and you pick which one you like better. Some people like the tabular method, some people don't. Okay, so notice here that if this was just x to the third, we would know how to take the derivative of it, because that derivative is just 3x squared. So the wishful thinking part, the part that we're going to call u, is just x squared plus 2. So u is x squared plus 2. If we take the derivative of u to the third power, because remember we're covering this up, it's like it just reads u to the third power, that would be 3u to the second power, and then we'll have another term multiplied on the end of it. So notice, just quick comparison with the formula. This part right here is this f prime of g of x, and this part right here is going to be g prime. And you can do this in any order, fill in the parentheses how you want. If I notice that the u is particularly easy, it's x squared plus 2, I can compute g prime in my head, it's just 2x. So I can go ahead and plug in 2x right there, there's the g prime part. Now the f prime part is this 3u to the second power, but we have to stop and ask ourselves, but what was u originally? U is x squared plus 2, so I'm going to plug in x squared plus 2, and this is my appropriate derivative. Now the tabular method kind of simplifies this. What I like doing is writing f, g, and h, because as you will notice in some of the homeworks, there's multiple compositions, and so there might be multiple chain rules. You make a little t-chart like this, and then what I'm going to do is I'm going to just look at the problem that I was given, and I'm going to break it down by trying to ask myself, what is the u portion? I'm going to write that in the g column, and then is there another composition in there, and I'll write that in the h column, and so on. So notice that the part that we had to like wishful thinking away was the x squared plus 2. Okay, and so I make another line underneath where I write that. And when I wish that x squared plus 2 away, what I was left with was something to the third power. So usually in the tabular form, you just write whatever this is to the third power. Like that's what I'm left with when I wish it away. And so we're using u over here. This table uses g. If you want to make it look the same, you can change this to u and v. So it'll say u to the third power. It's kind of just up to you how you want to do it. Fu and v, fg and h, doesn't much matter. So when we wished away the x squared plus 2, it left us with u to the third. When we wrote down x squared plus 2, we now have to look at that and say, okay, is there another thing in this that hints that there, like, if we considered this to be the problem that we were asked to take the derivative of, do we know how to do that derivative, yes or no? And if the answer is yes, you know how to do the derivative, then you can just stop right there and get on to the final result. If the answer is no, you don't know how to do the derivative, then it's possible that there's an additional chain rule on there, and I'll show you one of those in a second. So now all I have to do is take two derivatives the easy way. So if it was just u to the third and it was a practice problem in one of the earlier sections and I told you what's the derivative of u to the third, you'd say 3u to the second. Okay, cool, write it down. 3u to the second. But you're going to remove the u and replace it with whatever you see in the column diagonal to it, which is x squared plus 2. So I'm going to replace the u with x squared plus 2. Same thing, if you're in the, if you think about each of these like it's a column, if you're in the u column and you want to know what's in this blank, it's just whatever the derivative of that is. So that's 2x. Boom, we're done. The answer to this derivative will just be the bottom row all multiplied together and you're done. That's the derivative. So do this times that, you'll notice that agrees with our answer there. Okay. One last example where we might need to apply the chain rule more than once, and the easiest way, unfortunately, that I know of how to do this is to just use sines and cosines because they're easy to string together. If I ask you for something crazy, like what is the derivative of sine of the ln of x? Okay, so when you look at this, you say, well, I know how to take a derivative of sine, I know how to take a derivative of ln is just 1 over x, and sine is just cosine. But what I don't know how to do is sine of ln of x. Don't know how to do that. There's not a nice rule that we've learned so far that tells us how to do that. That means it's probably chain rule. So I like using the tabular method for this. I'll do f, u, and v. What we would like to wish away here is this sine of ln of x. If this just said sine of something, well, the derivative's cosine. I know that. Okay, so I'm going to write down this is sine of u. Cool. So what is the part that we wished away there? Well, it is the sine of the ln of x. But notice there, I've got to do some wishful thinking again. Like if I just ignore that outer part and I look at this, I say, okay, do I know how to take the derivative of sine of ln of x? Then the answer should be no. But what if it was just sine of something? Well, then the derivative would be cosine. So I'm going to write down that this is the sine of v. And what is the v? Well, the v is just the ln of x. So again, I'm like ignoring this part, looking at the ln of x. Do I know how to take a derivative of ln of x? Yes, it's one of the ones we've memorized. It's 1 over x, so we're good to go. Okay, so now what I need to do is the derivatives of each of these columns. And then remember that the u's and the v's and whatever, I have to actually go back and plug in what u and v is equal to. But notice here that u is equal to the sine of v, and v is equal to the ln of x, so u is just the sine of ln of x. And v is just the ln of x. And so sometimes I like to get a different color, and I'll write in the other way that I could write this. So when I'm plugging in sine of v, I'm actually going to write sine of ln of x, and when I'm plugging in v, I'm just going to write the ln of x. Okay, so the derivative of sine is cosine. But what is u? U is the sine of ln of x. Okay, so that's sine of ln x. What is the derivative of sine of v? Well, it's cosine of v, but what is v? V is just the ln of x, so I'm going to write down cosine of the ln of x. And lastly, what is the derivative of ln of x? It's just 1 over x. So when I'm ready for my final answer, all I have to do is write those 3 things in the bottom row down multiplied by each other. So the answer to what the derivative of this thing is, y prime, it's just going to be the cosine of the sine of ln x times the cosine of ln x all over x, because that 1 over x is just like dividing by x. And this is your answer. Okay, so I hope that this video kind of illustrates some of the points that were a little hand-wavy about the chain rule in the previous videos, and it is my suggestion that you go back and watch some of those videos involving the hand waves where I said, okay, so just take my word for it, this is what it is, and try to derive those for yourself. And I think you'll notice that the more and more you practice with this, the better and better you get. Some people are going to be formula people, some people are going to be tabular people. You need to pick whichever one works for you, and do not try to do both. Do one or the other, but not both. for Calculus 1 until you are absolutely sure you know how the chain rule works and you can catch when it is applied. The product rule applies anytime you're taking the derivative of a product of two functions of x. The quotient rule applies anytime you are taking the quotient of two functions of x. And the chain rule applies anytime you are taking the derivative of a composition of two functions of x. And it's really important that you learn how to distinguish between them. So in the practice homework assignments where these things get mixed up in the quizzes and the tests and what have you, my suggestion is that you take note of the way that these types of functions look, because a lot of times you should be able to just like glance at it and tell whether it's going to be a product, a quotient, or a chain rule. Remember, these are the rules of the game. You cannot get around them. They are always to be applied when you have the situation that they apply to. Two functions of x, and I tell you to take a derivative, it is product rule. You cannot circumvent that. Two functions of x divided, quotient rule, you cannot circumvent that. Two functions of x composed, chain rule, you cannot circumvent that. It's like a rule that you have to follow every single time, so you have to learn how to recognize it.